Hess's law. What is it? Luckily, we've done an intro, and it should be pretty straightforward. In going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. In other words, if there are 3 steps to a reaction, and we know the enthalpy of the first reaction and the second and then the third, we can actually just add those 3 steps together to figure out the energy of the overall. So here's a good example. N2 plus 2O2 yields 2NO2. The delta H for that is 68 kilojoules. This reaction also can be carried out in 2 distinct steps with enthalpy changes designated by delta H2 and delta H3. There they are. Notice those will cancel, and when added together, I can add the delta H values together to get the delta H of the third. The idea of Hess's law is you can take those 2 intermediate steps, like this, and add it to one giant step. If a reaction is reversed, the sign of delta H is also reversed. So if you have an exothermic reaction and you write it in the reverse, it becomes an endothermic reaction. The magnitude of delta H is directly related to the quantity of reactants. So therefore, if there's a coefficient in front of a compound or element, you would multiply the delta H by that coefficient as well. So let's look at this information. Notice the first one is ammonia breaking down into its 2 component parts, nitrogen and hydrogen. The other is hydrogen and oxygen combining together to form water. In the first reaction, you might wonder why there are fractional coefficients, but that's to force 1 mole of ammonia. So calculate the delta H for this particular reaction down below. So the next series of steps of this particular PowerPoint presentation are going to walk you through it. I'm then going to show you a shortcut method that can make things a little bit faster. Alright, the way to do this is to work backward from the required reaction using the reactants and products to decide how to manipulate the other reactions at your disposal. Reverse any reactions as needed to give the required reactants and products. Multiply reactions to give the correct numbers of reactants and products. So, back to that example again. There's the desired reaction. If we reverse the 2 reactions, this is what we have. Notice NH3 is now on the correct side, and H2O is now on the correct side. Multiply the reactions to give the correct numbers of reactants and products. In the first case, we would like 4 NH3, and you can see we have to multiply through everything by 4, which means we have to multiply the delta H by 4. What about the other one? Well, that we have to multiply by 3 because we want to get 6. Therefore, the delta H is multiplied by 3. Therefore, how to do it? Notice when I multiplied, I get these numbers. Notice how the hydrogens will cancel. And in the end, what do we have? Delta H of 1,268. Now, let me go back and show you the earlier question without the answers. Oh, there it is. And I'm going to show you how to do this the shorthand way. What I do is I actually look at each of the 2 steps. I know I have to add these 2 together in such a way to get this one down here. Oops, this isn't actually the first one, is it? Nope. Let me go back, because that's the reverse ones. Okay, here's the data. Now this is how I would do it. You notice that NH3 is a reactant here, and it's a product here. So I have to change the number 46 kilojoules. Not only do I need to make it negative, because I have to flip its location, but I have to multiply through this by 4. Then I have to look at the second equation, and I have to determine what to do with it. I find one thing it has in common with the one I'd like to get to. I look at this and this. Again, I have to flip the sign because the water has to be on the other side. I also notice if I multiply through by 3, then I will have the right number of water. Now, in AP chemistry, it is going to be important to verify that the other things will cancel, meaning, in this case, hydrogen, oxygen, and nitrogen, because sometimes you then have to add something else that would usually be listed. So, if I multiply through this by 3, of course, this is going to give me a 6, a 3 here, and a 6 here. If I multiply through by 4 here, I'm going to get 4 of these, 4 halves, and 2, which is like 2, and 12 halves of H2, which is like 6. Alright, now, when things get flipped around, the hydrogens are going to cancel. I'm going to be left with 2 N2 on the other side and 3 O2s on the other side. So you can notice that I've kind of verified the fact that these things will add together. We really don't care if there's more than one thing in common with the one given in the 2 in the question. We just want to make sure that they can add appropriately. If you actually have to add them together, you're welcome to do that. Let's go back again and look at the future. Let's go back in the forward and go past where we already were. So sometimes you're given the individual reactions and you're asked to find the delta H using Hess's law, or sometimes you are given the standard enthalpy of formation, delta HF. Again, something we did in intro. You can find the delta HF values sometimes in the body of your textbook or at the end of the textbook. The change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. So that would be like if we wanted to say A plus B yields AB. Notice there's 1 mole of AB. And it always shows the compound as a product. That's the delta HF. The reactants are elements, and elements, by the way, have a delta H value of 0 because you can't form elements, they simply are. Conventional definitions of standard states. So for a compound, for a gas, pressure is exactly 1 atmosphere, and for a solution, the concentration is 1 molar. Compounds have to be pure substances. For elements, the form N2 and K in solid in which it exists is 1 atmosphere and 25 degrees Celsius. The heat of formation is 0. So for elements, the delta HF is 0. Delta HF, remember, is heat of formation. How much energy does it take to form a compound from its elements? If you have an element, it doesn't take any energy because it is an element. It's not a compound. So that's why the delta HF value is 0. Here is a schematic diagram of these changes of energy in this particular reaction. You notice we are manipulating the reactants to become products. They're just being rearranged in some format to give something new and different. And the energy changes that accompany them. And they're showing you how you would calculate the energy values. Now, what we're going to do is we're going to think of some problem-solving strategies to use delta HF. When the reaction is reversed, the magnitude of delta H remains the same, but the sign changes, kind of like what we said before. When the balanced equation for a reaction is multiplied by an integer, the value of delta H is also multiplied by that same integer. and the change in enthalpy for a given reaction can be calculated from the enthalpies of formation from the reactants and the products. And the way you calculate it is the delta H of the products minus the delta H of the reactants. Elements in their standard states, remember, are 0. So let's look at this example. Calculate the delta H for the following reaction. And we're given lots of information. Notice they've provided very nicely the delta H values for sodium and hydrogen being 0. Sometimes books aren't that clever, and they don't tell you. And sometimes students, when they come to questions like that, think that you can't do the problem because you're missing information. But in fact, I know automatically, let me get the pen back, I know automatically that this is going to be 0, and this is going to be 0. Of course, it tells me this down here, but as an AP Chem student, you don't even need that listed for you because you know those values are going to be 0. H2O is negative 286, and NaOH is negative 470. And of course, we have to multiply by the coefficient. In this case, they're both 2's. How do we solve the problem? Delta H of the products minus delta H of the reactants. These are the products, so 2 times negative 470 minus whatever 2 times negative 286 is. Let's see if they tell you what it is. And it's negative 368 kilojoules. A very easy problem. It makes it a lot easier to figure out the delta HF values for things when you have, or the delta H for the reaction when you have the delta HF of the individual components. Most books, and I believe your book is similar in that the delta HF values are all listed alphabetically at the back of your textbook.